This is a little demo of the ChipSHOUTER, the current engineering version. So it's basically production ready now. We're just kind of doing some final testing. And I thought I'd update people on what's happened since you might have first seen it at CHES 2017. And we've actually had a number of different hardware revisions since then. So there's been no major changes, but a lot of functionality improvements. And I just kind of wanted to show you how it all works. So one of the things we've been trying to do is make it really easy to use in all sorts of lab environments. And so, for example, it can detect if you have your probe on the front end. So this is the danger end here. If you remove it, you can see it's detecting that there's no probe attached, so it will not arm. It gives it a little arrow tone there. It won't turn on the high voltage circuitry until we have some sort of probe attached. So we can attach a beefier one here. So there's there'll be all sorts of different sizes. Ultimately, attach a beefier probe, and let's go ahead and force it to rearm. There you go. And so there's a really simple sort of basically test buttons on the front that you can do arming, so that turns on the high voltage. You can see there's an indicator on the front there. The high voltage is on, and we can inject faults just directly. And so this is useful just for testing that sort of the fault injection is working, and we'll ship with a really simple test board to show that. But where it gets more interesting is, of course, when we're trying to attach to real targets and how we need to sort of scan for specific pulse parameters. And that's where this thing is trying to make your life a little bit easier. So let's look at some of the features around that. Number one is for monitoring. So there's actually a little voltage monitor port, and it's set up as right now it's 10-to-1. The final version will be a 20-to-1 scope probe. So if I go ahead and have the scope up there and turn the pulse on, we can see some pulse waveforms, and that's actually programmed with a bit of a unique waveform right now. We'll go through, but we can change around what that pulse waveform looks like. So we can actually see what voltages is being injected into the probe with this really nice 10 or 20-to-1 scope probe set up here. And to actually set the parameters, what we have is on this side of the device, there's a bit of a little interface here. So this little RJ12 jack can just plug in, and so you'll notice there's kind of these long cables. The idea being, if you have this mounted to an XY table, these can pretty easily be bundled together. And this just has a little isolated USB interface that we can use to talk to the device. So let's take a look at that real quick. Oops. And so over here, so this is right now the final command syntax is going to change a little bit, but basically we have stuff to set voltages, set pulse widths, and all sorts of stuff like that. So yeah, let's just make this do a really simple pulse. So right now it's actually doing a pattern trigger, so we can turn that off. And if we look back at the screen now, and we arm it, it's going to have a fairly simple, really narrow pulse. And so what we're actually seeing here is, when I moved this, the scope probe tips right now aren't the final version, so they are a little finicky. We have a separate design for the scope probe attachment. But you can see this just sort of big fat pulse getting inserted into the device. And we can see this is about 200 nanoseconds per div, so it's quite a wide pulse. And it's up there. You can do this on cursors if you want. So it's about 212 nanoseconds. And you can see it's up there about 400, about 400 volts. So we're getting a pretty reasonable pulse size. And we can just change that via the programming interface. So I can say set voltage, let's set it much lower. And do that again. And so you can see that the pulse is dropping way down there. And we can, in fact, so we can set a a repeat, or we could just hold this down, and you can see if I increase the voltage, I can set the voltage to back up. And you can see right away we're able to inject the higher voltage pulse. So it's nice having the programming interface here, and it's just this really basic really basic serial protocol. And this is done because it's very easy this way to interface with all sorts of stuff. You know, if you can send serial data, then you can talk to this. So MATLAB, Python, everything like that has this type of interface. And we can of course pulse and arm and everything through that. So. And we can set the pulse width. Let's set the pulse width to a little lower. So just zoom out so you see the whole setup here. Set pulse width 100, say. So when I'm setting this pulse, what it's doing is it's just adjusting an internal trigger. And this internal trigger has pretty coarse just widths that you might use. There is a more advanced trigger. So there's a more advanced trigger option called a pattern trigger. And what this does is this actually lets me specify. So if we just go back to the computer screen here, hopefully you'll be able to see. I'm going to say set fast trig. And I specified a pattern of 1s and 0s. So if I go 1 1 1 1 0 0 0 0 and then hit pulse, if we look back at the scope here, we see this, you know, that's the same thing. It looks like this pulse we just had, but what's actually happening is it's being built from those 1s and 0s. So we can either set a pattern or we can append stuff to it if we want to. I'm just going to set another group of 3 1s. So I set a group of 3 1s, and then I go ahead and pulse. And we can now see the, so this was a shorter pulse, the other one was 4, so then we had 3. So you can see that you can just build a moderately complex patterns this way. Now the only problem with this, how you trigger this, well, you can trigger it through the serial interface. That's not going to have great time available, or time accuracy. You triggered it obviously with the button. That's even worse. And there is a pin basically that you can use to trigger the trigger that pulse generation. So those are the 3 ways to trigger the built-in pulse generator. But the other thing, because you know you want to use this connected to regular test equipment, there's an SMA connector on this side, so not the danger end. This is, do not plug this into your scope. Is a, plug this SMA connector in. This is an input for you know, just basically low voltage serial going into your scope. So what I have here is this is actually connected to a arbitrary waveform generator on this this oscilloscope, and so I can turn on, I have it fed back into another channel here, and if I turn on the waveform generator, you can see there's a generated waveform at the top. You can probably just see, but the waveform that's being inserted, you can see in the yellow there. So that's again the voltage monitoring. So let's just turn off the other one because it's just getting in the way. And this is sort of nice because, you know, here we have a similar waveform, but I can do stuff like, I'm just using the built-in tools that are generating this arbitrary function. So I can, if I increase the frequency, it reduces the width of those generators, and you can basically go down to around 50 nanoseconds. So if we get the cursors up, you can see, you know, how quick, how narrow is this pulse, and it's around 50, somewhere in there, 50 nanoseconds. And you can see it's quite, like, we have a second pulse coming right here, 226 nanoseconds later, and it's looking quite well formed. So this is sort of a nice method, having this SMA input, because you can connect it to all sorts of test equipment. This can actually also connect basically directly to the ChipWhisperer glitch output. It has a basically built-in pull-up, so the glitch output will pull that down and trigger the glitch. So this lets you use the ChipSHOUTER with any of the ChipWhisperer tools pretty directly. You can also it will come with an adapter board basically that goes from the 20-pin connector to either this guy or this guy too. So yeah, that's just kind of a really quick demo of what the ChipSHOUTER capabilities are. So you can see we've tried to make it quite easy to use. So there's a lot of options on how you use it. This input here, you can switch a 50 ohm terminator just via the software. So there's a PCherm on off. So you can turn on or off this 50 ohm. You might, if I really quiet, maybe you can hear the relay click. So there's a 50 ohm terminator. Again, if you're connecting this to a signal generator, it's going to expect that. And you can also set it active high or active low. And this input here is actually hardware into the glitch triggering circuitry. So what this means is, if you're using an FPGA or something to generate this, you're not constrained by the microcontroller that's controlling this thing. That microcontroller is what's generating the pulses. Obviously, the microcontroller is going to have a little bit of time delay associated with it because you're going to have to trigger the microcontroller's routines that's then inserting the glitch. The other one up at the top here actually also has a current measurement probe, so there's voltage. The current measurement is just done via some of the shunt resistors to limit the current output. So the voltage is generally the most useful to verify the glitching is actually happening. And the voltage, both of these can be useful because depending on the probe characteristics, you may not actually be inserting the pulse you think you are. And so let's take a look at, well, let's stick with voltage for now. Oops, let's arm it. Okay, so we have this waveform, basically what we were inserting before. And I'm just going to go ahead and I'm going to switch this nice big beefy probe for a much smaller probe. And what we're going to find is, this guy, oops, and I left it on so you can see it faulted on me because you're not supposed to have it armed with no probe connected. And this is a really small guy, so it's probably going to saturate pretty quickly. And we're actually going to see that. So we'll just clear the fault by holding the button down. Done. And then arm it. So I haven't changed any of the pulse settings, but you can see what just happened here. The pulse is, looks totally different. And you can actually see where it's shutting off over here, but we're basically having effects of the probe itself is limiting what type of pulse can be injected. So the feedback circuitry is really critical to understand, what are we actually doing with the hardware. And I can turn on the, we can get the current monitoring input. So the current monitoring one's quite a bit noisier, but you can still see actually that's not looking too badly. It's very similar in waveform to the voltage monitor. So there you go. So there you go. That's sort of what we're trying to do with the ChipSHOUTER, and there's going to be a lot more details of it forthcoming. In particular, there's what I think are really interesting, another target for this guide that's going to help you understand the probe characteristics. We have a mounting bracket to mount this to an XY table, and we're also actively working on sourcing both a really low cost sort of manual positioning for just helping hold this in place when you're doing testing XY table, and a fully electronic XY table. So those details are going to be forthcoming. We'll probably obviously have another update on that, but in the meantime I thought you'd just be interested to see that the ChipSHOUTER does indeed work. It's sort of a working device that is getting pretty close to a release, so keep your eyes out for it.